Hello Chem 1A, this is Chapter 12, Lecture Video 5, our last lecture video in this chapter, and we're going to be talking about solids and phase diagrams. Now, before we get into solids, we're really only going to talk about two major parts of solids, and that is lattice energy and the two major different types of structures that we can have in solids, and that's crystalline and amorphous. There is a lot more material in this chapter in our textbook about solids, and most of it is only relevant if one, you are a chemistry major, and two, you're a chemistry major going into a very specific field called X-ray crystallography. So because of that, we're not going to go over a lot of what's in this chapter about solids. So if you have questions, please don't hesitate to reach out and I can help you with those, but we're not going to have homework on those topics that aren't covered, and it's not going to be on the test. But if you're interested, I do know quite a bit about X-ray crystallography, so I'm always happy to talk about it if you want. So let's talk about the structures of solids. Really, structures of solids can be broken down into two major types, crystalline and amorphous. So what's the difference? We should know the difference between them. Crystalline solids are incredibly well ordered. They have a repeating, definite structure that keeps repeating over and over and over again throughout the structure of the solid. They also melt at very specific temperatures, right? If, for instance, we wanted to talk about NaCl, sodium chloride, which is an ionic solid and is crystalline, it has a very specific melting point. It melts at a very specific temperature. We could list like, hey, NaCl melts at like 1500 degrees Celsius exactly, right? And that would be true. This is a distinct difference from amorphous solids. So amorphous solids, as their name kind of implies, do not have an orderly arrangement, and this is the primary difference between the two different types of structures. Because of their non-orderly arrangement, different parts of an amorphous solid might melt at different temperatures due to a difference in structure. For instance, rubber, you can't give a specific melting point for rubber. You might be able to give a range of melting points, like this rubber will melt from this temperature to this temperature, somewhere in between there. We don't know for sure. And in fact, some parts of the rubber might melt at lower or higher temperature than other parts because of the amorphous nature of the structure. So let's talk about lattice energies. One thing we are going to talk about with solids is their lattice energies. So there is a crystal structure for compounds that are in the solid state, and they typically, what we say is they build what we call a lattice. Ionic compounds have incredibly high melting points, and substances with really high melting points are going to have really large lattice energies. And the lattice energy is really the strength of the crystal structure. Now we're only going to be talking about lattice energies for ionic compounds and the trends involving that. Now, lattice energy for ionic compounds increases with two variables, one being the increasing charge. The larger the charges within the ionic compound, positive or negative, doesn't matter, the larger your lattice energy. And this is the more important characteristic. So, for instance, if I'm comparing CaS to CaCl2, this guy wins, even though this guy wins because this is 2 minus and this is 2 plus, whereas this is 2 plus and each one of these is minus 1. This minus 1 versus the 2 wins. We don't even have to look at the next part of our trend. Charge is the most important of the two trends. The second trend is decreasing atomic radius. So the smaller your radius, the larger your lattice energy. But this only matters when we have a tie between two compounds for the charges involved, right? So maybe I have Mg2 plus S2 minus, right? So I have CaS versus MgS. MgS would win because they have the same charges and Mg is smaller than calcium. But otherwise, we wouldn't even care about the radius. So let's look at some more examples of that using numeric values and all that fun stuff. But you should know this trend. So we look at LIF's lattice energy, and these are all in kilojoules per mole.
If we compare that to LiCl, notice that the lattice energy went down. And this is because these guys both have a positive one, negative charge, positive one, negative charge, but Cl is bigger. So the lattice energy decreases. The same thing is going to be true of LiBr. LiBr will be even smaller than LiCl. Same charges, larger ionic radius in the case of the Br. So smaller lattice energy. Lii would be the lowest of this series. If we do this with magnesium, though, you see that the charge dramatically jumps between these two. We're almost 3 times larger in magnesium fluoride's lattice energy than lithium fluoride. And the reason for this is because magnesium has a 2+ charge, whereas lithium has a +1 charge. Then we see the same trend resulting between Mg and the other halogens, right? As we go down that column, the lattice energy for magnesium attached to a halogen decreases, right? Cl is smaller than F, Br is smaller than Cl, and so on. But notice that even the largest halogen attached here is still a bigger lattice energy than the smallest halogen with lithium. And this is because of that 2+ charge. It's why we care about charge way more than size in general. All right, so let's talk about phase diagrams. And this is the last topic of chapter 11. So phase diagrams are basically graphs that graph where the physical state boundaries are. We have some important vocab that we should know for these, right? So this is a phase diagram. It's effectively just a graph. Now, normally you'd have like axis numbers here so you could tell on both the X and Y axis. We usually have temperature on the X, pressure on the Y in a phase diagram. Now, these black lines here that I'm coloring in red indicate a change in physical state. They are where we have our boiling points and freezing points and sublimation or deposition points occurring, right? So for instance, if I was here and I moved to here, I just melted my solid because I went from the solid state to the liquid state across that line. And this line here between these two represents the melting point of our substance at each individual pressure. Now, you need to know generally how to label these. As a rule of thumb, as we go to lower temperature on the X, we go from gas to liquid to solid. So I would expect you to be able to fill in which is which on a diagram, right? I might not tell you, hey, this is the solid, this is the liquid, or this is the gas. I probably wouldn't tell you that. You'd need to know, hey, this is the highest temperature region, that's gas for sure. This is the middle one, liquid. This is the lowest temperature region. It's got to be the solid, right? You should know the names for our physical state changes between any of these 3 physical states. So if you're going from a solid to a liquid, that's called melting. If you're going from a liquid to a solid, that's called freezing or solidification. If you're going from a liquid to a gas, vaporization. Gas to a liquid, condensation. Solid directly to a gas is sublimation. Gas directly to a solid is deposition. You need to know all those guys. Finally, we have a new vocab word called a triple point. The triple point is the point at which all 6 of those physical state changes are occurring at equilibrium. So at the same time I'm melting, I'm also freezing, I'm vaporizing, I'm condensing, I'm sublimating, and I'm depositing all at the same time when I'm at the triple point. It's the point that the 3 different physical state lines meet. Some substances have more than one solid crystal structure and therefore will have more than one solid area. I won't make you fill in like guessing which one's which in any type of way on tests or quizzes for that. But I like this diagram. It's the diagram for carbon because it shows the actual axis labels, right? Like these. And some of the questions you might have on these are, hey, you're initially at a pressure of 100 atmospheres and 2000 Kelvin. So we'd go, okay, hey, that's here, right? At 2000 Kelvin, 100 ATMs. What physical state change occurs if you heat the substance at 100 atmospheres of pressure to 5000 Kelvin? So in other words, I'm changing from 2000 Kelvin to 5000 Kelvin. This is the new spot I'm in. So what physical state change occurred when I heated without changing pressure to get to 5000 Kelvin? Well, we went from a solid to a gas, so we sublimate, or sublimation occurred. We could also say, hey, you're at 5000 Kelvin, 100 atmospheres of pressure. What if we raise the pressure to, I don't know, 10,000 atmospheres of pressure? Well, then we're up here. What physical state change occurred? Well, we went from a gas to a liquid. That's condensation, right? So these are some of the types of questions you might be asked on tests or quizzes about physical state diagrams. One other important characteristic of our phase diagrams is this slope of the solid liquid line. So the line between the solid state and the liquid state, whether its slope is positive or negative, actually tells you something very important about that liquid substance, specifically its density.
Okay, so when we look at the phase diagram for water, something very important actually is present, and that is the liquid solid line here. Let's use a different color. The liquid solid line here. Now, if we look at the slope of this line, right? The slope of this line is negative. And hopefully we can see that just by the graph, right? And this actually means something specific about our substance. It tells us that the solid state is less dense than the liquid state. Phase diagrams that have a negatively sloped liquid solid line are always going to have a less dense solid state than the liquid state. And the primary reason for this is because as we increase pressure, our substance will always become more compacted and therefore more dense. And if, let's say, we're at this point in our phase diagram and we start to increase pressure, at some point our substance will go from the solid state to the liquid state. This tells us that in the liquid state, the substance is more tightly packed together. In other words, more dense. This isn't just true of water. It's true of any phase diagram that has a negative solid liquid slope. The opposite slope would mean the opposite density, right? So negative slope means solid state less dense than the liquid state. Positive slope for this line would mean that the solid state is more dense than the liquid state. All right, if you have any questions, please don't hesitate to contact me. This is the last slide in this chapter and the last video in this chapter. And as always, you can always reach out to my office hours in Zoom, or we can schedule a one-on-one Zoom meeting if you need help.